Now, if we put weights on the graph, let's say we're going to be using a graph to represent a map for argument's sake, right? And A is where you have halfway tree for argument's sake. Now, from halfway tree, you can get to, let's say, Manor Park, and the distance could be something. Let's say, imagine that the points represent places, and the edges would represent the distances between places. So from halfway to Manor Park is about 5 miles, 3 miles. About 5. Let's say this may be Ligani. Let's say about 3 miles. Let's say this may be Mona. 2 miles. And let's say this may be Papine. About 1 mile here, 2 miles here. Let's say the government is planning to put in some one-ways to try and increase our gas usage so that they can get more tax. So let's put in a distance from Papine back to halfway tree. That's 3 miles. Now I'm going to call this G2. So we're going to draw the adjacency matrix and the adjacency list for G2.
What is it?
G2 is a weighted graph, so adjacency matrix will be weighted. Although, quite often when you hear them asking for the adjacency matrix for a weighted graph, it says weighted adjacency matrix. So, the rules for populating the matrix now will be slightly different. If there is an edge from a source to a destination, then we'll put the weight in that position. If there is a self loop, meaning that you can get from A to A. So if this is a place, to get from A to E, we'll take 5 miles. To get from A to A would be 0 miles. So the weight from A to A will be 0. Now, by default, there's no way to, without going through something else, there's no way to get from A directly to C for argument's sake. So weight from A to C would be infinity. So A to A is 0, A to B is 2, A to C infinity, A to D 3, A to E is 5. B to A can't get there, infinity. B to B 0, B to C 1, B to D infinity, B to E infinity. After a while it becomes easier to just look for the edges, drop those in, and then infinity the rest. If it's a sparse graph. A sparse graph means that you don't have a lot of edges. In a dense graph, you have more edges. Now from C, you can get to A and nowhere else.
3.
That's 3. You have a self loop here. And infinity the rest. From D, you can get to C. 2 self loop there, everything is infinity. From E, you can only get to yourself, everything else is infinity. For the weighted adjacency list, we just simply modify this and include the weights. So A to E will be 5. A to D, 3. A to B, 2. B to C, oh, we didn't add one edge there, so I'll put 15. B to C is 1. C to A, so we did have one edge added right here. This node that goes to A with a weight of 3. B to C, the weight is 2, and E has nothing from it. Alright, now we've actually done questions 1 and 2 from the tutorial sheet. Now, question 2 makes the same assumption that we did. It actually laid the same framework that we did, where our graph represented a situation where the edges, the weights on the edges represented costs. Because to get from one place to another, you have a distance, and that's really an indication of the cost to get from one place to the other. Now, suppose weight had represented capacities. Let's say we had an application where different companies involved in some kind of loan scheme, and the weights represented the amount of money that one company would allow people to lend to another company. Now, in that case, how much money, and let's say within a company, I mean, there's no limit because it's your money. So in that case, what would be the weights for the self? How would you represent the self loops? That would be infinity. And if there's no relationship between two nodes, then you'd have 0. So the point there is that depending on what you're doing with it, whether to put 0 and infinity there will all depend on the context. But most sides will state, but unless otherwise stated, assume the weight mean costs. Alright? For this course at least. Alright. We haven't done the DFS yet, so we can't answer question 4 yet. Now, we're asked computer to square the adjacency matrix. You remember how to work with matrices, how to square matrices, right? Row by column? Alright, we won't actually do that one. But there's a point in this question that it might be useful to remember. If you square the adjacency matrix, not the weighted adjacency matrix, it's the basic adjacency matrix. If you square that, oh, you don't have that question?
The question what? It's not this one.
Yeah, look at the question section.
Stop at 3.
It stops at 3.
Has been updated.
Let me see.
No, it stopped at 3.
Okay, 3 is actually what we're doing.
Okay.
So, if you compute the square of the adjacency matrix, you actually get a 1 in the places where you can move from one node to another in 2 hops. If you cube the adjacency matrix, the entries that are 1 show the nodes that you can get from a source to a destination to in 3 hops. And it continues in that routine.
How much for 3? How much for 3?
If you get the cube of the adjacency matrix. So if you multiply the adjacent matrix to get the adjacent matrix to the 4th power, then we get the amount of places you can get from one node to another in 4 hops. So that's what that means. Alright. Now we're going to be looking at traversals of the graph. Graphs normally are useful to represent data, but they also can be used to implement rules. And when you're moving from one place to another, the fact that there's an edge between the 2 different points can actually be a useful indication of whether or not you should. And in moving from one place to another, the basic term is called a graph traversal. There are several types of graph traversals. 2 of the most opposite ones are the depth first traversal and the breadth first traversal. We're going to be looking at those first. There are also 2 of the simpler ones. Now, the depth first traversal is a visiting strategy where you try to search as deep into the graph as possible before you look around you. Now, think of a scenario where you move to a new neighborhood and you look to the first person you see. Well, you take a quick look around you, but the closest person is the person you go to. Now, once you're at that person, you may look around them and say, okay, oh, a nice car. Person looks like they make nice cake. Then we go to that other person. So you don't really care about your original neighbors. You're only visiting from that neighbor that you had gone to. Now, the depth first traversal, the basic strategy is to visit the neighbors of your neighbors first, before you even care about your own neighbors. The converse of that, as I said, the breadth first is sort of like the opposite of the depth first, is that in the breadth first search, or the breadth first traversal, you visit all of your immediate neighbors first, before you look at any of the neighbors of your neighbors. Now, to get the breadth first search done, you could actually keep a list. And when you look around you, you add people to the list in the sequence in which you see them. So when you decide that you're going to discipline yourself only to visit the people in the sequence that they're entered on the list. So you'd end up looking around you first, getting a list of all your neighbors, and then visiting all your neighbors. And now, once you're at each of your neighbors, you look around you and add those other neighbors to the list.